Lighter kid. Okay, Aditya, good morning. We will start today. Let us try to give in these 2 hours, let us try to give the complete revision of thermodynamics. That's our idea, right? That's our basic idea. Good morning, Suhas. Yes. So we shall start with first temperature conversion. I mean, we will go for the basic quantity in thermodynamics, the temperature. Yes. What is temperature? What is temperature of a body? It is degree of hotness or coldness of the body. It is degree of hotness or coldness of the body, right? So the temperature scale goes like this. This is ice point called freezing point of ice. This is boiling point of water. What is the temperature? 0 degrees Celsius, 100 degrees Celsius. The difference is, come on, 100. 32 degree Fahrenheit, 212 degree Fahrenheit. The difference is 180. 273 Kelvin, 373 Kelvin. The difference is 100. So what's the temperature conversion? Come on. Temperature conversion is degree Celsius minus 0, because the lowest one is 0 degree Celsius. So this is degree Celsius. Degree Celsius minus 0 divided by the difference 100 equal to degree Fahrenheit minus 32 divided by the divisions are 180 equal to Kelvin minus 273 divided by the divisions are 100. The divisions are 100. Please look at. Yes. Now, if you want to convert degree Fahrenheit, if you want to convert degree Fahrenheit from degree Celsius, what's your idea? Cross multiply this. What you get is 9 by 5 times degree Celsius plus 32 is Fahrenheit. If you want degree Celsius, suppose, come on, if you want degree Celsius, suppose cross multiply this, 5 by 9 times, come on, degree Fahrenheit minus 32. This is the most of the time we use, this conversion only most of the time we use. Sweta, could you hear me now? Reply me, please.
Yes, sir.
Very good. Shall we proceed? Please remind me here and there, wherever we have, wherever I miss some topic, please remind me, right? Let me go ahead. Yes. Shall we go ahead? So after temperature conversion, what do we take for in general on heating? What's the expansion? Expansion on heating, what we call as thermal expansion. Come on, shall I go ahead to thermal expansion? Come on, thermal expansion. Thermal expansion. Thermal expansion. Come on. In the case of thermal expansion, thermal expansion, if a metal rod of length L0 at 0 degree Celsius, at 0 degree Celsius, 0 degree Celsius is now heated to T degree Celsius, right? Length L at T degree Celsius. So this is what is increase in length. Yes, this is what is increase in length, delta L. So L minus L0, what we call as increase in length, L minus is equal to L0 alpha delta T. L0 alpha delta T, where L0 is initial length at 0 degree Celsius, alpha is the temperature coefficient of, come on, temperature coefficient of thermal, come on, otherwise coefficient of thermal expansion of solid, and delta T is rise in temperature. So what is alpha? Alpha is thermal expansion, coefficient of thermal expansion of the solid. What's the value? Come on, L minus L0, come on, L minus L0, L0 into delta T. This is alpha, right? Right, Kanna, Harini, could you hear me? Yes. Sriram. Sriram wants me to teach something new today, right? He doesn't want revision. So, am I right, Sriram? Sriram wants me to teach something new today, right? He wants to continue with the topic. Yes. Am I right? Yes, come on. So, alpha is the temperature coefficient of thermal expansion of the solid, or simply coefficient of thermal expansion of the solid. Then comes areal expansion. Suppose this is a rectangular area at the time when the temperature T equal to 0 degree Celsius, right? 0 degree Celsius. When the temperature T is equal to 0 degree Celsius. Rectangle of area A naught at 0 degree Celsius. Now on heating, it becomes longer, area increases A. The similar principle you can apply. What is that? Delta A is equal to A minus A naught equal to, come on Kanna, A minus A naught equal to A naught alpha delta T. A naught alpha delta T. Instead of alpha, now we are going to use, come on, beta. What is beta? Coefficient of areal expansion. Temperature coefficient of areal expansion of the solid. We have very clearly proved that beta is equal to how many times alpha, Kanna? Beta is how many times alpha? Come on.
2 alpha.
2 alpha, yes. We have already proved it. Beta is equal to 2 alpha. I did not get any reply from Sriram. Sriram, put it on chat box. Then comes volume expansion, right? Then comes volume expansion. If its volume V naught at 0 degree Celsius, and suppose V at T degree Celsius, where delta T is the rise in temperature, suppose delta T is the rise in temperature, increase in temperature, maybe 50 means 0, 50 degrees rise in temperature, then V is equal to V naught into 1 plus gamma delta T, where gamma is temperature, come on, temperature coefficient of volume expansion of the solid, and we have proved that gamma is 3 times alpha. Gamma is 3 times alpha. Now the most important thing for today, what is the volume expansion of gases? Do we have any knowledge on that? Do we have any knowledge on that? Yes. Do we have any knowledge on volume expansion of gases? Come on, Sai Siroba, please. Mukesh, Mohan, coefficient of volume expansion of solid. No, volume expansion of gases I am talking about. Come on, because thermodynamics is after all study of gases. Yes. Do we have any good knowledge on coefficient of volume expansion of gases I am asking? Come on, yes, put it on chat box. Put it on chat box, please. Yes or no? Are you thorough with volume expansion of gases? Are we thorough with volume expansion of gases? Come on. Yes. Sai Surba say yes. Coefficient of volume expansion of gases. Yes. How we are going to deal with that? Let us see. So, next topic I want to take expansion of gases. This is what mostly we will be using it in our thermodynamics, right? So, here is a gas enclosed in a container, you heat it. it's a gas enclosed in a container, you heat it, you supply some quantity of heat. Now will it expand? No, because if my container is strong enough, probably the gas is not allowed to expand. This is what in thermodynamics in future we are going to call, in another half an hour we are going to call it as specific heat at constant. We are going to constant volume. Excellent. We are going to call it as specific heat at constant volume. Suppose the gas is just free to move. The gas is just free to move up. In this condition, you are heating it. We are going to call it as specific heat at constant pressure because it is free to move. The pressure remains same inside. We are going to call it as constant pressure. But now what I want to take only this constant pressure. Yes, this is a container. V0 is the volume of gas at 0 degree Celsius, suppose. V is the volume of gas at T degree Celsius, suppose. Now our rule says that V minus V0 or V is equal to, come on, the same V0 into 1 plus gamma delta T. Yes, this is what we have been using. But what's the delta T? Can any of you help me? Because I am clearly using degree Celsius, not Kelvin, right from the beginning. What's my delta T? Which is nothing but T degree Celsius. This is nothing but T degree Celsius because you started your experiment at 0 degree Celsius, now you are somewhere at T. So change in temperature is naturally T degree Celsius. Come on. So V is equal to V0 plus V0 gamma T degree Celsius. Or you can call it as delta T, nothing wrong. That's your choice purely. Either you call it as T degree Celsius or you call it as delta T, that's purely your choice. But preferably as of now we stick to degree Celsius. Right. Now what is this gamma value for the ideal gas? What is the gamma value for this ideal gas? This is our interest today. Yes. What's the gamma value? Anyone please put it on chat box. What's the gamma value for an ideal gas? What is gamma? Temperature coefficient of volume expansion of the gas. Temperature coefficient of volume expansion of the gas. Can you tell me what is gamma value? Come on, I'm waiting on the chat box please. What's the gamma value for an ideal gas? Come on. What's gamma value for an ideal gas? Come on. What is gamma value for an ideal gas? Come on. Gamma value for an ideal gas. What is gamma value for an ideal gas? Come on. What is gamma value for an ideal gas? Can any of you tell me? I never discussed this in my class. Am I right? Come on, tell me. Sweta, did I ever discuss this in our class? Yes? We discussed, you mean, right? We did?
Actually, what you are saying here comes in?
Right. Now I want to take volume here. I want to take here temperature in degree Celsius. Temperature in degree Celsius. Now at 0 degree Celsius, this is 0, 0 suppose. At 0 degree Celsius, do I have volume of the gas in the given container? Whether the gas possesses some volume in its container at 0 degree Celsius? Yes or no?
Yes, sir. Yes.
Definitely yes. Definitely yes. Yes. Then what's the nature of graph I am going to get? What is the nature of graph that I am going to get? Paklama, this is going to be my graph. This is going to be my graph, right? This is going to be my graph. This is my graph between volume and temperature. So clearly what I want to tell you now is, come on, this is my volume V0 at 0 degree Celsius. Look at 0 degree Celsius volume V0. So I have some box, dabba, say aluminum box, where I have got gas. How much gas is there? Come on. Volume of V0 at at
0.
yes, 0 degrees Celsius. Good. I am heating it to some temperature, say T. This is V at T degrees Celsius. Now, what is the expression for this V? That is what is given here. V is equal to, come on, V naught plus V naught gamma, say T degrees Celsius or delta T, that is your choice, already I told you. Right. Now, this equation is a straight line equation very clearly, because Y is equal to, look at Y, this is Y axis, Y is equal to, come on, C plus mx. So, this is x axis, no doubt. Look at x axis, x. This is y axis, V naught, y intercept, of course, V naught, y intercept. Now tell me what's m value. What is m value? Please tell me what's m value. The m is nothing but m. Yes, m is nothing but V naught gamma, equation number 1. V naught gamma is the equation number 1. You got the point? How I arrived at this? M is equal to V naught gamma. How did I arrive at? You understand thoroughly from the graph? Yes or no? Yes, please.
Yes.
Yes. Priyanka Vardhini says that I have already given the gamma value for steel. Of course, I gave you alpha, beta and gamma values for steel, but I never gave you gamma value for gas. Today we are going to find it. Gamma value for gas. What is gamma? Coefficient of volume expansion of gas. Right? In our last classes, we have discussed about solids, but we never discussed about, come on, gases. Right? Come on. Now, can any of you tell me what is m in mathematics? What is m in mathematics? Slope. What do you mean by slope? Tan theta. Let us go to mathematics. Slope is nothing but tan theta. Come on here. Tell me what is tan theta here? Theta. Opposite by adjacent. Come on, tell me what's m. Come on. V minus
V naught.
Very good.
By T minus 0.
Simply T degrees Celsius, because minus 0. This tells you that m is nothing but V minus V naught by T. If you substitute this here, V minus V naught by T is equal to V naught gamma, again this will lead you to this equation. You will come back, nothing new you will get. You will get the same equation. So, no surprise, nothing I have done. So, I am just making one cycle of the equations. There is no use. Am I right? Once you calculate m and you substitute here, again it takes you back to the original equation, where we started with. Am I right? Please check it. If you cross multiply this and you put this V naught the other side, you get the same equation. This equation you get. Am I right? Yes or no?
Yes.
Yes. There is no use. Then there is no use of this long discussion. But I can do one thing. Yes. Now you look at. Yes. Now you look at this triangle I want to take. This is after all theta. Now do tan theta. Tan theta m. Come on, chal karna. Opposite, what is that? 0 V naught, what is the distance? 0 V naught, what is the distance? Come on. V naught. By this side, where the volume is supposed to become 0 according to us? In the matter around us, when we operate with 0 Kelvin, the volume should become 0, pressure should become 0, temperature is 0, all is 0, but that is not possible. Therefore, this is 0 degrees Celsius, this is 273 degrees Celsius with minus, or call it as 0 Kelvin, because we know pretty well at 0 Kelvin the volume should become, come on, 0. Then what is this distance, tell me now? (273). Now tell me, m is given by this. Of course, when you calculate slope, we don't bother about minus plus. Our concern is just opposite by adjacent, that's all. We are interested in length of the line segment. We are interested in length of the line segment. We don't bother about minus or plus, right? That's what is trigonometry. in trigonometry, when you talk about sides, we need not talk about sine. Okay, now come on, Kanna. Now tell me, copy this there. M value, what M value you get now? Slope, what did you get now? New, come on, V0 by 273. Right, what is the M value? What is the M value there? Come on, what is the M value there? Come on.
V0 gamma.
V0, sorry, V0 gamma. Now we are getting an interesting result. Gamma for any gas and every gas is, come on, English சொல்லுங்க, V0 cancel, what is left with? Come on.
1 by 273.
That is the value, 1 by 273.15 exactly for any ideal gas, take it granted. Coefficient of volume expansion of the gas, the coefficient of volume expansion of the gas is 1 by 273, provided it is an ideal gas. Got it, Kanna? Got it? Please put it on chat box, yes or no, please. Yes, please put it on chat box, yes or no. You understood 273, not minus 273, it's just 1 by 273. You got it or not? So this is what we are going to use in the case of coefficient of volume expansion of the gases under constant pressure. Come on. Why I am putting the condition constant pressure? If the pressure is there, again the work will be done in overcoming the pressure. Yes? Come on, I am waiting on chat box. Srinidhi put yes, Suhas yes, very good Kanna, very good Kanna. Kartika Balaji put yes, Bhargav yes, Sai Sivaruba. One more time please, okay. She wants me to explain one more time. I hope you understand this equation, V is equal to V0 into 1 plus gamma delta T. V is equal to V0 into 1 plus gamma delta. This first place I want to equate this equation with a straight line. Therefore, I have done it. Y is equal to mx plus c. Where it is clearly proved that m is nothing but V0 into gamma. Of course, I have written here V0 into gamma. Look at this is equation number 1. Then I want to look at the graph. What is this m? M is nothing but a slope tan theta. Is nothing but slope tan theta. So when I want to calculate tan theta of this triangle, I get opposite by adjacent. We can be very sure about this temperature because only at 0 Kelvin the volume will become 0. Volume will become 0. Therefore, it is 0. Therefore, it is 273. This is 273. And this is V0. This is V0. Right? We know very well. Therefore, V0 by 273 is what is slope. According to the given equation, m is given by, again slope is given by V0 into gamma. By comparing these two, you get V0 get cancelled. You get that gamma is equal to 1 by 273, exactly 273.15 in the case of any ideal gas. In the case of any ideal gas. Got it now? Yes, I got okay from. Very good, excellent. Now, what's our next topic? The most important part of our thermodynamics. What is that? We have been telling. Next, I can discuss something about melting, boiling, latent heat. Shall we discuss this particular topic, or straight away I will jump to kinetic theory of gases? Which you prefer? Please tell me on chat box. Please tell me on chat box. Shall I go ahead latent heat, specific heat, latent heat of fusion, latent heat of vaporization, all these concepts shall we cover? That may take around 10 minutes or 20 minutes. Or straight away I can go to kinetic theory of gases and go for thermodynamics. Which is better? Come on.
Small gist you can give, sir.
Sorry, Kanne?
One small gist you can give, sir.
Sir, the definition for
Definitions will do. Okay. Some of them on the chat box they are telling directly we can go to kinetic theory of gases. Please others please respond me. Shall we have a complete discussion of latent heat, of fusion, vaporization, all those? Or straight away we can go to kinetic theory of gases. What is preferred? Come on, come on. Lot of kids here on the chat box, they are telling straight away go to kinetic theory of gases. That's what a lot of children are telling. Others please respond me. Shall we discuss about latent heat, latent heat of fusion, latent heat of vaporization, method of mixtures, all those, or directly kinetic theory? Come on, put it on chat box, please. Please, Kanna. So most of them wanted. Varun says we will go in order. Kinetic theory also will complete. Come on. First kinetic theory and then we will come back. A lot of students are telling. First we will complete kinetic theory and then we will come back. No problem. I am keeping one topic pending for you, that is conduction, convection and radiation. You may remember. Conduction, convection, I mean heat, how the heat flows in solids, how the heat flows in liquids and gases, how radiation happens. Only after teaching radiation I can take you for Newton's law of cooling, right? Newton's law of cooling? Yes, Newton's law of cooling is pending. So, adala irukku. So, on the time eduthukalam. Jyoti Krishna says that latent heat will teach. Okay? Enakana latent heat teach pantu poyilama. Lot of the kids wanted kinetic theory. But anyway,
Sir, no need to do it fully, sir.
Just a guest. Very good, Kanna. What she is advising, what? Sure, Kanna. I will complete in maximum 5 minutes. Don't worry. I will complete the what you call latent heat, everything maximum in 5 minutes. Don't worry. Yes, Kanna. Please come back here. So I want to take. You can also use one full page. Please use one full page of your notebook. Maybe the tilted horizontal part. I mean landscape position. Yes. Now I want to take here temperature, maybe degree Celsius or Kelvin, your choice. Here the quantity of heat that you supplied or time. Your choice. So some solid is kept on LPG stove, the timer is on, the quantity of heat is supplied to the solid, and we want to draw the graph between. You put one thermometer inside that solid container, right? Now the solid is getting heated. Temperature increases, your time is going to run non-stop. So this is 0,0. You keep supplying, your LPG stove keeps supplying heat also. So the first, what will happen? As the time passes, temperature should increase, time should run. Yes, that's what is happening. So this is solid. Temperature, you can understand, temperature increases. Come on, temperature increases and time runs. It goes like this. This is solid, temperature increases. So in this region, what is delta Q? Heat that you supplied is equal to, come on, mc delta T. Yes, this is delta T. Delta T1 let us call. So this point stopped. What point it is? That's a point where your solid started melting. Yes, so this is the melting point clearly. So this is melting. So this is the melting point, temperature of melting, right? Temperature of melting started. Now will your temperature increase? No. Now your ice started melting. In your container 50% ice, 50% water, but still your thermometer reads same 0 degree Celsius, right? Right, 0 degree Celsius. So again, 75% of the ice melt, 25% of the ice remains, even then your thermometer reads 0 degree Celsius. Here your 100% ice got melt, everything got converted into water. Now your temperature is likely to increase. So in this region, what is happening? Melting is happening. If it goes like this, melting, also called fusion, right? It's going on. Now between this point and this point, you supply heat. Yes, you definitely supply heat to where it's gone, ml. where L is latent heat of, come on, fusion. For melting, how much energy you need, that's what is delta Q, where latent heat of fusion of ice or water, how much is this, come on?
336 into 10 power 3.
Excellent, into 10 power 3 joule per kg. Joule per kg. Got it? Got it, Kana?
Yes.
Good. Now, what happens when the entire ice got melt? Now it is 0 degree water ready to increase its temperature on heating. Yes, you keep heating it, your watch keeps running, your temperature starts further ascending up. Yes, your temperature is ascending up now. Right? This is the region where the temperature increases, and again at a particular point the temperature stops. The temperature stops, right? The temperature stops. Where the temperature is supposed to stop in the case of water? Water like any temperature? Yes, this is 100 degrees Celsius. What we call as boiling point. What we call as boiling point. So, to rise from 0 degree water to 100 degree water, right? 100 degree water, what we call as boiling. Boiling, yes. How much heat you should have supplied? The quantity of heat that you supplied is given by mc delta T, where delta T is, where C is specific heat capacity of water. Specific heat capacity of water, of course. What's the value of C in the case of water? Is approximately 4200 joule kilogram per Kelvin per minus 1. Yes, this is specific heat. Water is getting heated. So, heated. The water is getting heated in this direction. Right? It's heated. Right? This is solid. Inge heated. Heated. What is being heated here? Solid. Then what is the specific heat of solid? Specific heat of ice? Specific heat capacity of ice?
2100.
Yes, 2100 joule kilogram per minus 1 Kelvin per minus 1. Excellent, Kana, that's right. Now go to, now the water started boiling. The water started boiling. So temperature is not going to increase, but you keep heating it because your stove, your watch is non-stop and your stove is continuously on, LPG stove. You keep supplying heat. Yes, come on, tell me now. Here you supplied some quantity of heat, delta Q, 4. Where gone this heat? It is nothing but LF, no, vaporization. ML, last time it was latent heat of fusion, it is latent heat of vaporization. All of you know what is supposed to be the value of latent heat of vaporization. Latent heat of vaporization is given by, come on, 2260 into 10 power 3 joule kilogram per minus 1. Joule kilogram per minus 1. No, okay. Correct. Joule kilogram per minus 1. Perfect. Am I right? Correct. Perfect. Then this process is called what? Can any of you tell me what is this process? What process is happening here? Vaporization. Very good. Here the vaporization is happening at 0 degrees Celsius. Now you keep heating, finally everything becomes gas here. Here everything becomes gas. There is a difference between vapor and gas. What's the difference between vapor and gas? What's the difference between vapor?
The vapor has both water and.
So you guess the answer? Vapor has got more water and gas doesn't have water. Of course, if you heat something from water, out of ice, it must have water molecules. What else it can have? It should have only H2O, nothing other than that. Right? Nothing other than that. So this is again the next level of thermodynamics. There is a difference between vapor and gas. Really, there is a difference, but it is out of our scope as per our textbook. But anyway, I will try to tell you. If you keep on increasing the temperature, can you increase the steam temperature? Steam is generally 100 degree. In our mama's kitchen, it is 100 degrees Celsius, the steam. But you can increase it, already I explained you. By putting it in pressure cooker, you can increase the temperature of the steam to even 120 degrees Celsius, 140 degrees Celsius. In industries, they are heating it to 500 degrees Celsius, 600 what? Steam. So you can increase the temperature of, come on, steam. So when you keep on increasing the temperature of steam, you will reach a stage where you can no more liquefy it. Means the vapor which cannot be liquefied is called gas. Okay. This is slightly more level than our thermodynamics syllabus, but I don't want to go beyond that. Okay, fine. Come back. I hope you understood.
Vapor did you discuss, sir?
Sorry, Kanna?
Specific heat of vapor.
No, we don't discuss specific heat of vapor. We discuss only specific heat of gas.
Yes.
Yes, we don't discuss specific heat of vapor. We don't discuss. In our syllabus, we don't discuss specific heat of vapor. That is a bit tricky. Specific heat of vapor is a bit tricky. That depends on many parameters. Whereas specific heat of gas is simple. Another number syllabus specific heat of gas is given, right?
Yes.
Yes.
If we heat that steam means that cooker itself will blast, no, sir?
Definitely, because it will be keep on trying to expand. At one point of time, probably the cooker may burst, provided your burner is strong enough. It's giving huge heat at a time. But if your burner gives less heat, continuously it will expand. But in the case of pressure cooker, there will be some release point. If there is no release point, definitely the pressure cooker will burst. மேல அந்த வெயிட்டர்னு ஒன்று வச்சிருக்காங்களே அந்த ரிலீஸ் பாயிண்ட் இருக்கணும். If the release point is not working properly, definitely is bound to burst, however small your flame may be, right? Right, Kanna? Very good. So we have completed this also in one stroke. Yes. Now we can come back. We already spent 5 or 10 minutes on that. Anyway, is it okay? Did I see? I took water ice as an example. Don't take. You can do the same thing. It is a steel solid. It is a molten steel. It is again the molten steel is added. At one point of time, steel will start vaporizing. Imagine, steel will start vaporizing. Yes, you will get steel gas. It is possible. Anything can be melt, but only thing the temperature difference may be very high. Say for example, in the crust of sun, every metal exists in the form of, come on, in the crust of sun. This is the core of sun. This is the crust of sun. Sun, you can imagine what's the temperature, where all the metals like our aluminium, all the metals exist here in the form of vapor. Clear now? So it is possible, even the metals can be vaporized, please believe me. Even don't think that only liquids can be vaporized. Even metals can be vaporized. But you need a huge temperature like thousands of degrees Celsius. That's it. Got the point, Kanna? Got it?
Specific heat of gas.
Specific heat of gas. Well, anyway, we are going to take up, no? CPCV, that's our basic syllabus. Anyway, we are going to take up, don't worry. Specific heat of gas we will take up. Preferably after, should I complete that also now? Murchilla my CPCV? Not a good idea. We will have some knowledge of that, pressure and all, and then we will take up.
Yes.
Yes, shall I clear the board? Shall I clear the board, please? Tell me yes or no?
Yes, sir.
Yes, please come back. Yes. Now we want to start with pressure exerted by gas. Pressure exerted by a gas on the walls of the container. So I want to start with a rectangular block, our usual method, I hope. But this time I will go fast. I don't go slow like last time, because whatever we have covered nearly in the last 10 classes, today we have to cover in one class. Okay, come on. Now, there are, first of all, kinetic theory statement. Kinetic theory of gases statement, please. Kinetic theory of gases statement, please. Statement of kinetic theory of gases, please.
Like the particles of the gases will be freely moving and will be colliding with the walls of the surface.
Yes, 1 second. 1 second, here something, screen, yes,
Statement or the points?
just 1 second, Kana. The screen is slightly troubling me, 1 second, I will check that, what exactly it is. Yes, it is working well, okay. Now, what are the statements of kinetic theory of gases? All the gas molecules are alike, they are very small, perfectly elastic spheres, they are very small and perfectly elastic small particles, okay, molecules. Come on, first point, they are alike, they are very small, they are perfectly elastic, rigid bodies. Yes, come on, continue.
The volume occupied is
Excellent. The volume occupied by the gas molecules is highly negligible with compared to volume of the entire container, and then they move in,
They move in all
random
the
motion.
definite patterns.
yes, they move in all possible direction with all possible velocity. They move in all possible direction with all possible velocity. Yes.
Except for
collide with
They,
each other.
during the random motion, they collide on each other and collide on walls of the container. So when they collide on the walls of the container, so the collision is perfectly elastic. The collision, whatever may be, the collision is perfectly elastic, and collision time is negligible. How long they remain in contact is negligible. How long they remain in contact is negligible. Collision time is negligible, and finally, when they collide on the walls of the container, they rebound. Thereby, they create change in momentum. Thereby, they create force. In turn, it becomes pressure. Therefore, they exert pressure on the walls of the container. So, because they are moving in all possible direction with all possible velocity, if V is the velocity of the gas, the given gas molecule, this may be divided into Vx, Vy and Vz, Vx, Vy and Vz. Therefore, V vector equal to, come on, Vx vector, Vy vector, Vz vector. So, V vector equal to Vx I cap, Vy j cap plus Vz k cap. But when you take RMS velocities of this along x axis, along y axis and along y axis in the mathematical language, the probability of velocity along x, y and z, which is greater, all are equal, because already we stated that the molecules can go with all possible velocity in all possible direction. Therefore, all of them are equal. Therefore, Vx modulus square must be equal to Vy modulus square, Vz modulus square, provided you measure square root, right? What we call as root mean square velocity. What we call as root mean square velocities of all this. These are root mean square velocities are equal. You the square எடுத்துட்டாலும் okay தான். Even if you remove this outer square, it doesn't matter. Okay. So Vx square bar, Vy square bar, Vz square bar. So means when you want to calculate RMS velocity, V square bar is equal to 3 times Vx square bar. So Vx square bar, I mean this bar refers, anyone help me, this bar refers, yes, average 3. This you can take it granted. This you can understand by using the concept that the molecules can have all possible velocity in all possible direction. That's the basic idea. Yes. Done. Now I can go ahead with my, once you are thorough with this, I can go ahead into the derivation part of it. Shall I move inside the derivation? Come on. Shall I move into the derivation? Yes, yes.
Today we will be doing the Carnot also, sir.
Everything will complete, everything will complete. We will go fast, don't worry. We'll cover. Whatever I have done in the previous classes like 1.5 hours, today I will complete in 10 minutes or 15 minutes. We will go. Okay, now take a particular, choose a particular molecule which is going with the Vx, Vy and Vz. Let us take Vx alone. The particle goes along.
Individual velocities won't be equal.
No, not at all. Only the average can be equal, not the individual. Individual may have different velocities. No. Now I take a particular molecule. Therefore, it collides on the wall and rebounds. Therefore, change in momentum of my molecule along x-axis is given by 2m Vx. I hope you understand this. Hope you understand this. Change in momentum is given by mv minus of minus mv plus 2mv, right? Change in momentum. This, therefore, what's the collision time for my particle? What's collision time for my particle? Because I have taken only x-axis, forget y, forget z, it has to go like this. Therefore, the time taken is, the distance is 2L between the two collision, velocity is Vx. Therefore, force on my particular single particle, for a single particle, what's the force is given by change in momentum by time taken. Change in momentum by time taken. Therefore, force on single molecule is given by, come on, mvx square by L is the force on the given single molecule, right? How many such molecules have? How many such molecules have? Therefore, total force along x-axis means anybody going along x-axis should go and collide on yz plane, should go and collide on yz plane. Okay, anyway, force along x-axis is given by, come on.
Isn't it minus Vx?
Of course, that's your choice. That's purely your choice, which you take. Of course, in general, we take this as positive. In general, we take as this as negative. Good. Minus 2mx you can take, right? Minus 2mx. Okay, fine. So, minus mvx square by L force. How many times?
n times.
N times. Then force on the wall. This is on the particle. Particles. This is wall. Particles, plural. All particles. All particles. This wall. Come on, just the plus of this. Plus mvx square by L n times. Yes, this is the force. Then force per unit area is called pressure. So pressure along x-axis is given by n times mvx square by L cube. Area, L square will be attached to the denominator. So you get pressure. Then this Vx can be replaced with this quantity.
It's plus for the wall because it's in the opposite direction.
Of course, you are right. Because the wall experiences force in this direction, whereas your molecule is being pushed back in this direction. Very simple. Not necessarily it should be taken as, you can take this as negative, this as positive. That's your choice. Okay, come on. Now pressure along x-axis is given by, come on. Pressure along x-axis is given by, come on, n times m divided by volume. What is Vx square? Average.
V square.
E by 3.
3.
V square by
Yes, this is your final expression pressure. There is no point in talking about x, drop it, because once you talk about pressure, there is nothing called pressure along x-axis, pressure along y-axis, in the concept of kadayadu. According to Pascal's law, pressure in the given fluid, liquid, gas is same everywhere, right?
So how you got L cube, sir?
Sorry?
L cube.
Because this is force per unit area is pressure, no? Here, when I move from here to here, I divide with L square, the area. Between this step and this step, this is force, this is pressure. So I have to divide with L square. So I got it, right?
your fx, you have done that change in momentum, sir.
This is change in momentum. Final,
Yes, sir.
final momentum minus initial momentum. Final momentum is minus mvx. Initial momentum was mvx. So you got it, right? See, I am here.
2 mvx into.
Okay, today I am moving with the speed that you are already aware of this. My idea today is to give kind of brush up, not exactly fully teaching that. Yes, come on, please refer your old notes. So this is the pressure. What pressure we have got now? Formula for pressure, what we have got now? Come on.
N into M.
Yes, pressure is always given by 1 by 3 Nm by V into V square bar is the pressure, exerted by gas on the walls of the container. Pressure exerted by gas on the walls of the container. Got it? Shall we move ahead? Come on.
This is YZ plane.
No, once you talk about pressure, there is no need of talking about YZ plane or any plane, because pressure is a scalar quantity. Pressure prevails everywhere in the given gas, Other than a Pascal's law. Pascal's law says that pressure in a fluid in equilibrium is same everywhere. That's what is Pascal's law. So after calling it as pressure, it is meaningless to put x here. It's meaningless. This x doesn't carry any meaning. Once it is calculated for x, it is equally applicable for y as well as z or anywhere. Got the point?
Yes.
Come on, pressure is this much. Then I want to go ahead for 1 mole. Then this n becomes n 6.023 into 10 power, provided I assume 1 mole of gas. Now my box, my aluminum dabba has got how much gas? Come on.
1 mole.
1 mole. Then your pressure becomes 1 by 3 Nm by V into V square bar. Who is this Nm? Provided you accept N is a 1 mole. If you accept N is a 1 mole, then what's N into M? Which is nothing but molecular mass of that particular gas. Suppose I am filling hydrogen in my container. Suppose my container has got 1 mole of hydrogen. What's this M value? Hydrogen H2. 2 gram. It's nothing but 2 gram. Had I got nitrogen in my entire 1 mole, what's this M value? M value, nitrogen
14 grams.
14 grams. It goes like this, 1 by 3 pressure. Yes, this is what is. Now you cross multiply this. Yes, what you get? Come on. Yes, pressure P is equal to PV is equal to 1 by 3 M V square bar. Now what is PV for 1 mole? What is PV for 1 mole? Yes, therefore V square bar 3 RT by M. No, I want only V RMS. It is square root of 3 RT by M. 3 RT by M, right?
The RT, that is kinetic energy.
Sorry?
RT we got from kinetic energy.
No, PV is equal to RT for 1 mole.
Yes.
You are right. Equation of gas equation. PV is equal to mu RT. You are right. Where mu is equal to 1, right? So this clearly shows that your RMS speed of the gas is directly proportional to square root of temperature and inversely proportional to, come on, inversely proportional to molecular mass. For example, in this box, in this single box, there are hydrogen molecules. There are, say, oxygen molecules. For example, oxygen molecules. Now, what is the ratio between velocity of hydrogen and velocity of oxygen molecules in the same box dabba? What is that? Is nothing but, come on, because I'm taking same box, the temperature is supposed to be same. I need not give you that the temperature is same. You can understand, because they are in the same box, temperature must be same. Come on, now your velocity is inversely proportional to molecular mass. Come on, molecular mass of oxygen, hydrogen, square root of 8 is the answer, 2 root 2 is the answer. Got the point?
Yes, sir.
This is speed of the gas. We can change the temperature also. Accordingly, we can compare. We can compare accordingly. Got the point? Please check it. So now we arrived at some equation for RMS speed. V RMS is equal to square root of 3 RT by M, where here M is the molecular mass. Yes. Now, V most probable square root of 2 RT by M.
So
We,
the DH2 and by DO.
sorry Kanna?
So that DH2 by DO.
Oh, you want this? Should I bring it back?
So can you tell?
Oh, it's very simple, Kanna. See, RMS speed is inversely proportional to square root of m. So I am talking about hydrogen and oxygen. What's the molecular mass of hydrogen? M2. Molecular mass of hydrogen 2 gram. So it goes to inversely proportional to 2. Oxygen 16. It is inversely proportional. Ulta ho gaya because it is inversely proportional. Look at. That's all answer. That's all answer. So what answer I am getting is the ratio between velocities of hydrogen and oxygen in the given box or box kulla given box, because in the given box temperature must be same. Suppose you are having two different box, then the question paper setter has to tell you what's the temperature in first box, what's the temperature in second box. Got the point? Our temperature will also figure at the time. This will also figure in the calculation, but now it is not figuring because I have taken same box. Clear now?
Oxygen molecular mass is 32 or 16.
Oh, that's a problem. Oh, 16, correct. 16, 8. Oxygen, what's the molecular mass of oxygen? Kana O2?
Hey, one oxygen is 16.
Yes, you are right, Kanna. Oxygen, correct one. I only made mistake. I took this atomic number I took. That's a mistake happened. Very good. You are right. So 32 by 2. So it comes out to be a square root of 16, which comes out to be 4:1. Good. Very good, Kanna. Excellent. Very good. An atomic number put. Good. Very good. Please take note of RMS speed, most probable speed and average speed. Please take. So we have completed everything about kinetic theory. Almost we have completed everything about kinetic theory, right? Everything about kinetic theory. We should move on to, once we are thorough with kinetic theory of gases, we have to move on to, come on, in connection with this we have to understand degree of freedom, because we are talking about molecules. Next, it is better to talk about degree of freedom. Come on. What is the meaning of degree of freedom of the given gas? Come on. What's the meaning of degree of freedom of the given gas? Degree of freedom. Come on, what do you mean by degree of freedom? Maximum possible independent movement. Maximum possible independent movement. Maximum possible independent movement of the gas, of the given gas, is what is called degree of freedom. Once again, the maximum possible independent movements of the gas is what is called degree of freedom. Say for example, a single molecule in this room moving like this, it has got freedom to move along x-axis, y-axis as well as z-axis. So the degree of freedom is naturally 3.
X, Y, Z, 3 times.
Yes, x, y and z. This is x, y, z, right? So that the degree of freedom. Therefore, for monoatomic gas, degree of freedom is 3. For diatomic gas, once you take a diatomic gas, for example, I take this as a diatomic gas. Look at this as diatomic gas. Now it can move x-axis, y-axis, z-axis, all those 3, and it can rotate like this. Now it's rotating about what axis? Can you help me? In our usual convention, now this is rotating about what axis? Look at my blue color pen. This is axis. Y-axis. Axis can be only one. Y-axis, right? It's rotating about y-axis. Now I can rotate it about z-axis. Now the same scale. Now I can rotate about z-axis. Look at. Yes, I am rotating about z-axis. Now I try to rotate along x-axis. Is it meaningful or meaningless?
Meaningful.
It is meaningless. It is meaningless. What's the reason? Why it is meaningless? Can any of you tell me?
Because you are rotating in this way, sir.
Moment of inertia is 0, sir.
Excellent. Moment of inertia is 0. Moment of inertia is 0. Yes, you could understand. Someone is asking how can I attend the class in Zoom. Here only 2-3 students we have permitted, not in Zoom. Okay, okay, good. Now this is when the scale is rotating like this. Say this is your diatomic molecule, like hydrogen, another hydrogen. This is the diatomic molecule. If it rotates like this, its moment of inertia is 0. Excellent, connects. Moment of inertia is 0. Therefore, you should not count it. So you can count along y-axis rotation, you can count along z-axis rotation, you cannot count along x-axis rotation. Therefore, you get only 2. So already you had x, y, z 3, now rotation 2, altogether it becomes 5. Then what is law of equipartition of energy? What is law of equipartition of energy? This law is very simple. The total kinetic energy, not total energy, the total kinetic energy available for the given molecule is shared by all the degrees of freedom equally. In other words, in simple language, the kinetic energy associated per degree of freedom for any molecule is, come on, of? No, simply of RT per mole per degree of freedom. For 1 degree of freedom, this is the value. Suppose for monoatomic you have 3, just multiply this with 3. For diatomic you have 5, just remove this and put 5. Right now, I mean multiply with 5. The entire equation should be multiplied with 5 in the case of diatomic molecule, right? So what is it with the kinetic energy per mole per degree of freedom? Come on, per mole per degree of freedom. Come on, of RT. Once again I tell you what is the law of equipartition of energy. The statement is so simple. The total kinetic energy available is equally shared by all the degrees of freedom. All the degrees of freedom. The other way around, when you say in the other way around, what is that? The kinetic energy associated per degree of freedom per mole is, come on, of RT. So I will write here clearly, kinetic energy per degree of freedom per mole is simply of RT.
So this we got from half MV RMS equals
yes, exactly. Already we proved that of mv square equal to 3 by 2 RT, where you have got 3 degree of freedom. Therefore, per degree of freedom, this is the answer. Very simple. You are right. Right? This means for 3 degree of freedom. Therefore, 1 degree of freedom we are talking about. Then divided by n both sides. What is where n is Avogadro number 6.023 into 10 power 23 Avogadro number. Come on, divide panna enna agum? Kinetic energy per molecule, instead of n number of molecule in 1 mole, now you get only 1 molecule, right? Per degree of freedom. One molecule ke evlo varum? Appo enna pannom? This side is to be divided with n. What is R by n? Yara solunga paakalam. Where k is Boltzmann constant, where k is Boltzmann constant. R is gas constant. Now let us recall. I think some of you have some doubt. I am not getting clear reply from you. Therefore, I doubt whether you are aware of this what I am teaching now. So come on the chat box, please put me yes. Borger puts off KT, very good. Sai Surabha also understood the concept. Yes. Boltzmann constant, very good, excellent Kana. Now, kinetic energy per degree of freedom per mole is simply of RT. Kinetic energy per molecule per degree of freedom. எவ்வளவு கண்ணா யாராவது ஹெல்ப் பண்ணுங்க? of kT, or equal to 8.31 into 10 power minus 23, sorry 8.31 மட்டும்தான் joule mole power minus 1 Kelvin power minus 1. It's a standard value, universal constant. Similarly, the K value, come on, யாராவது சொல்லி பார்க்கலாம், நான் சொல்லி கொடுத்தல எப்படி கண்டுபிடிக்கணும், joule Kelvin power minus 1. Understood this? Any doubt, please put it on chat box. Should I reteach this, or are you thorough with that? Please put yes or no chat box. Please reply me on chat box. Please reply. Please reply. Clear? Clear? Anyone else please? Clear? Not clear, Sai Suriba, not clear. What's your doubt? Sugos clear? Sai Suruba clear? Okay, very good, very good. Clear? Okay, okay. Good, 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 good. Others may please put your fingers. Give me on chat box please. Bhargav, yes. Yes, yes. Kartika Balaji, yes. Anyone else please reply. Please reply Kannam. Harini, yes, clear. Excellent, Sai Surubha. Jyoti Krishna, clear. Others please put your fingers fast. Young kids, come on fast. Afsal, clear. Very good Kanna. Afsal, clear. Very good. Others please. Be fast please. Okay. So now you understood thoroughly what's the kinetic energy per mole, per molecule, and how the degree of freedom works. Now I want to give a simple tabular column very fast. I may take only 5 minutes. I guess you will not have any doubt what I am going to do. Now a simple tabular column for you. Yes. I hope some of you can even help me in doing this. Yes. Monoatomic, diatomic, trilinear, triatomic linear, diatomic, monoatomic, right. Then triatomic non-linear, triatomic, last one is triatomic non-linear. So it's like this. Right. Degree of freedom. Monoatomic 3, diatomic 5, triatomic linear 7, non-linear 6. Now kinetic energy per molecule. Kinetic energy per molecule. I am not talking about mole, per molecule, the entire molecule. Come on. 3/2 kT, 5/2 kT, 7/2 kT, 3 kT. Now kinetic energy per mole.
Sir, degree of freedom formula is used.
Yes, I will give right now. Let me complete this alone. Come on. Kinetic energy per mole is simply given by 3/2 RT, 5/2 RT, right, 7/2 RT and 3 RT, right. Then how do we get this degree of freedom? How do we get this degree of freedom formula? Here we get this degree of freedom, F is equal to, come on, 3n minus C, where C is number of constraints you have, n is number of atoms, C is constraints. number of atoms and constraints. C is the constraints, number of constraints, right? So what do you mean by constraint in physics? Which is nothing but the number of bonds in chemistry, suppose. So this fellow, suppose he is having only one bond, but he is having 3 into 2, 6, 6 minus 1 bond, so 5. He is having 3 into 3, 9, minus 2 bonds, therefore 9. Here 3 into 3, 9, minus, here is one hydrogen bond. So altogether 3 bonds, so 9 minus 3, 6. You can extend this to even polyatomic molecules, any molecule, even for the chain of atoms, you can extend it. Come on, you understand now kinetic energy per mole, which is nothing but half mv square, bar. This is nothing but, what is the formula for this? Half mv square bar. So this m is mass of one molecule, whereas this is molar mass of the given gas, molar mass of the given gas. Got the point, Kanna?
For molar mass, we need to use RT, sir.
Sorry, Kanna, something is going on, sorry. Yes, sorry, Kanna, for molar mass we should use, come on, Kanna.
RT, sir.
Of course, that's what you see now. Please check back. I'll take you back. Yes, you look at here. For 1 mole it is RT. For 1 molecule it is, look at KT. Why? When you want to go from 1 mole to 1 molecule, you divide by capital N. Where capital N, when R is divided with capital N, you get this answer, K. Got it? Got it, Kanna?
Yes, sir.
Yes. Now,
right, can you show sir that side?
Right, this side you want me? Okay, come on. You want still further?
No sir, enough sir.
This is enough. Okay. Please check it. If you want very clarity here, I thought you may be aware of that. So, you clear up K is equal to R by N. This is a universal constant. All of them are universal constant. N is universal constant, R is universal constant, K is a universal constant. Everything is universal constant, right? R is the gas constant 8.31, K is a Boltzmann constant 1.38 10 power minus 23, and N is Avogadro number 6.023 in 10 power 23.
Sir, the freedom of molecules of triangle non-linear arrangement.
Freedom of molecule, come on. Triatomic non-linear, come on. Here 3 3s are 6, sorry, 3 3s are 9, minus 3 constraints, 3 bonds are there, therefore totally 6.
Okay.
So you must be aware of this, then only I can proceed further for the next topic. What is supposed to be a next topic? Can any of you help me out? Put it on chat box. What's my next topic supposed to be? Thermodynamics will enter. So once we step into thermodynamics, usually our idea first to understand some terms related to thermodynamics. What are they? First, what do you mean by system? Collection of large number of molecules. A balloon filled with hydrogen, good example for system. Your cycle pump having in the cylinder, cycle pump cylinder, the air is got trapped, so very good system. Petrol vapor is there in the car engine, in your car engine, ready to burn, that's a very good system. So any collection of any gas is what is called system. Collection of any gas is what is called system. Got the point? Collection of any gas is what is called system. Now what is surrounding? Anything other than the system is called surrounding. Suppose today I am interested in my hydrogen balloon, but for the hydrogen gas inside the balloon, everything around this, including my body, it's a surrounding, is surrounding, anything around that is called surrounding. Clear now? Everything is surrounding. So system and its surroundings, right? And then how many systems we have? Open system, closed system, isolated system. Open system, which is free to move, in the sense even the gas molecules can come out of the hydrogen balloon, means it is open type. Open vessel cooking at your home. Amma on the satti vechittu appadi soodu pandranga. That's a good example for what? Open system, where the molecules can go out or may come in, whatever may be. That's open system. Closed system, molecules cannot escape. Already there are 5 moles of gas, it got trapped inside your system. that is it. You heat it, you cool it, whatever you do, that 5 moles will remain constant. This is called closed system. Then isolated system, the same 5 mole now got trapped, but you can't heat it. Why? Heat will not go inside because it is isolated, thermally isolated from the surrounding. Clear now? So, heat exchange between the system and the surrounding is not allowed. Once again, heat exchange between the system and the surrounding is not allowed. Then we call it as, isolated system. Then certain terms associated with thermodynamics. What are the terms associated with thermodynamics we are going to learn? Come on, thermodynamical process. What do you mean by thermodynamical process?
Sir, then how can we say about adiabatic, sir?
Adiabatic delta Q 0, that is all, pakka, it is isolated. So, isolated system is what is called adiabatic, that is all. You are right, you are right. Right. Now, clear kana? Now, we want to talk about thermodynamical variables. What are the thermodynamical variables? Anything that you can measure as a physics student, anything that you can measure as a physics student is a thermodynamical variable, anything, your choice. What? Yes sir, I can measure pressure, I can measure volume, I can measure count the number of molecules, I can measure the mass of the gas molecule, and I can measure anything else, temperature, I can measure how much heat goes in, I can measure how much heat comes out, how much work is being done, all this, whatever you name it, density, choice, that's your choice, you can name it. Sir, there are 10 molecules, there are 20 molecules, okay, 10 molecule is a system, all these are thermodynamical variables. So, thermodynamical variables, anything that you measure, something about the thermodynamic system is what is called thermodynamical variable, correct? Then, what about when there is a change in thermodynamical variable, that is what is called? When there is change in thermodynamical variable, that is called? You can put it, you can put it as, put on chat box. When there is change in thermodynamical variables, it is called, come on, please. When there is change in thermodynamical variables, suppose pressure changes, volume changes, what we call in thermodynamics, come on. Suhas, why don't you put Suhas, please? My dear kids, please put it on chat box. When there is, I think today I kept a lot of time delay, it looks. That's the reason why kids could not interact with me instantly. I will correct it by next class. When there is change in thermodynamical variable, it is called, yes, Mukesh gave me correct answer. Mukesh Mogan gave me correct answer. It is a thermodynamical process. Yes, Sai Sivarup also gave me. It is thermodynamical variable. I think today chat box I kept time delay of 60 seconds. It looks. It takes very long time. Very good, Kana. Very good. Very good. So it is a thermodynamical process. So today our topic is mainly regarding thermodynamical process. Okay, poillama thermodynamical process poillama. Isothermal, adiabatic, isochoric, and isobaric. Right? And the board easier complete. We'll try to complete as maximum as possible. Probably today I may not be interested in doing some derivations, but not very many derivations are there. In the process discussion lab, we don't have much of derivation. But only one thing, even before we go to the discussion, yes, Kana, almost all of them are thermodynamical process. Excellent, Kana. Sai Siruba, Suhas, Harini, Bhargav, lot of things. Good, Kana. Now, before entering into thermodynamics, we want to understand the difference between internal energy, heat supplied, work done. We will try to understand this and then we will go inside. Come on. What is heat supplied? Suppose this is your system. This is your cycle pump. Let us take it. This is your cycle pump. It contains some gas. Say for example, you have got nitrogen gas, for instance. You have only nitrogen inside this. Now you are supposed to pump it like this, but now you are heating it. Therefore, it is going to expand. It's going to expand. Yes, Kana. Now what I am going to do, first point, I want to supply heat to the system. Heat supply pannilama. Shall we supply heat to the system? Yes. I want to supply heat to the system. Come on. I want to supply heat to the system. Delta Q. I supply to the system. Is it positive or negative? Anyone help me? Is it positive or negative? Anyone help me? Positive. What's the formula for this? Delta Q supplied to the gas may be written as, come on, mu times C delta T. This C is meaningless because heat supplied to the gas at any point of time can be divided into, come on, two cases. Delta Q under constant pressure is given by mu Cp delta T. Delta Q under constant volume may be defined as mu, come on, mu delta Q under constant volume.
CV delta T.
Yes, mu Cv delta T. So this is delta Q, positive. So now you supply heat. Now the question arises whether you heat the gas under constant pressure or constant volume, you will take it under the process. But now the piston moves up, it is doing work. What is work done by the piston? Integration P dV. Integration P times dV, right, is the work done by the piston, work done by the piston. Is it positive or negative in this case? If it is, yes, clearly my arrow mark shows that it's expansion, it is positive in my case, Then the internal energy, delta U. What is the definition of internal energy? The sum of all the kinetic energy of the molecule is what is called internal energy. ரொம்ப simple answer, for internal energy of 1 mole, what is the sum of kinetic energy of all the molecules? Very simple answer, provided it's monatomic. Ana ennoda example inga na enna eduthurukken, come on, nitrogen, diatomic. Appo naanga enna podnum, exactly, that's all, mudije pochu internal energy. But what I wanted is change in internal energy. This is internal energy, look at, this is internal energy, but what I am interested in, change in internal energy. What is change in internal energy? 5/2 or change in temperature. Because I am heating by using LPG stove, probably the temperature of my system has gone from 30 degree to 100 degree. In the case, suppose let's take it granted, this is an example, 30 degree to 100 degree. What is delta T at the time? What is delta T at the time? Come on. Come on. 5/2 or delta T for diatomic, right? This is internal energy. So increase in internal energy is positive, decrease in internal energy is negative. Now on the other hand, what I am going to do now, I have cycle pump or heat pump or maybe petrol engine, diesel engine, something. I remove heat from it, delta Q. Is it negative or positive? Anyone please help me? Heat removed is positive or negative? I take away heat from, please put it on chat box. If I remove heat from the system, it is positive or negative? It is negative. For example, your engine is running, your car engine is running. Your car engine ever releases heat to the surrounding? Have you ever seen that? Car engine releases heat to the surrounding ever? Yes or no? Have you seen minus delta Q in your day-to-day life? Yes or no? Please put yes or no. Suhas, please put yes or no. Negative, have you ever seen your car engine delivering heat to the surrounding? Have you ever seen? Of course, it is always yes. Why? Without leaving heat in the silencer at the back side of the car, your car can never run. So the heat, the smoke that is coming out from your car engine at the back side of the car is what is this. You understand? You understand? By leaving heat, the temperature of your car engine has slightly decreased or increased. By delivering the what you call the hot air, what we call as smoke, at the back side of the car, your car's engine temperature would have slightly decreased or not? Yes or no?
Yes, sir.
So that is decrease in internal energy. That is nothing but decrease in internal energy, which is negative. That is negative. Then what will happen to a piston? The piston would have moved down, therefore that is negative work done. That is going to be negative work done. So there again I start from here, supplying heat to the system positive, increase in internal energy positive, work done by the gas is positive. work done on the gas is negative, decrease in internal energy is negative, removing heat from the system is negative. Got the point? Got it? Yes. What are the various formula for delta Q? Probably we end up with these two formulae for delta Q. Good, take note of that. Then what is internal energy? Most of the time internal energy is a function of kinetic energy, not most of the time, all the time. Therefore, the internal energy is always given by F by 2 times RT for 1 mole. 1 mole. How many moles you have, accordingly you can put, where F is number of degree of freedom that particular gas, of that particular gas. Got it? Come to work done. Work done is always given by integration PdV. Integration limit may be V1 to V2. Very clear. Expansion of the gas, work done is positive. Compression of the gas, work done is negative. Increase in temperature of the gas, internal energy is positive. Decrease in temperature of the gas, internal energy is negative. Heat supplied to the system, positive. Heat removed from the system, negative. Each one has got its own formula. Please check formula for heat, formula for internal energy, and formula for work done. Please check it. Please check formula for internal energy, all those.
Yes.
Good. Now I can go ahead with my explanation. I can go ahead with my explanation. Yes. Now this is my cycle pump system, let us say. I fix it here. Now what is constant? What is constant because I fixed it? What is constant because I fixed it? Yes. Now I supply heat, I put it on LPG stove and heat it. I supply so many joules of heat. Now delta Q is equal to mu CV delta T. So mu CV delta T is the quantity of heat that I supplied under constant volume, According to first law of thermodynamics, please look at, according to first law of thermodynamics, come on, according to the first law of thermodynamics, delta Q is equal to delta U plus delta W. Heat that you supply to system is made use for two purposes. Number one, it can increase the internal energy. Number two, it can do the external work. Both the possibilities are open. Is it necessary that when this is positive, this must be positive, this should also be positive? Is it necessary? Come on. When heat is supplied to the system, you put your system on LPG stove, heat it. Is it necessary, is it compulsory that both internal energy and work done should increase? I mean positive. Come on.
No, sir.
Not necessary. Very good, excellent. Because when you put a system on LPG stove and heat it, there might be increase in internal energy. It may not do work. When, say, pressure cooker, fixed, it won't do any work. In the pressure cooker case, this is 0. Because it is not expanding. Because it is not expanding, the formula integration PdV, dV becomes 0. Therefore, it is not doing any work. Appo enga pochu ninga kodutha heat mottamu, the entire heat that you supplied gone to, come on.
Internal energy.
Therefore, in the case of constant volume, come on, what is your conclusion now? Delta Q under constant volume is equal to mu CV delta T is also given by 100% goes to internal energy, no work is done because dV is 0, because this is 0, work done is 0, it is not doing any work. The entire heat that you supply goes only to internal energy. What is the internal energy formula? Come on. F by 2 RT. Because you multiplied here with mu, here also you can multiply with mu. Because the other side you multiplied with mu, here also you can multiply. Otherwise you can take 1 mole, mu will be 1. Now tell me, mu cancel. Delta T cancel, supposed to be delta T. then CV is equal to F by 2 R. So it's a standard value for a monoatomic gas. CV is equal to 3 by 2 R. Diatomic gas, CV is equal to triatomic linear. I think I can go there. I kept some space there for this purpose. I can take you back to the tabular column somewhere here. Yes, here already I kept one. Yes, I am keeping one vacant for that. Yes, look at here. Now tell me CV, monoatomic gas.
3 by 2.
Yes, this is molar. This is 5 by 2 R. This is 7 by 2 R. This is simply 3 R. This is simply 3 R. Now all of you are very familiar with the Meyer's relation, I hope. What's the Meyer's relation? Cp minus Cv is equal to? What is Meyer's relation? Cp minus Cv is equal to R. Therefore Cp is equal to Cv plus R. So now I want to talk about Cp. Come on, what is Cp? Cv plus R. Cv is 3 by 2 R. Then it is plus R. Yes. This is 7 by 2 R. This is 9 by 2 R. This is 4 R. No, plus R, plus R. Plus R. Because Cv plus R, right? Now we'll go for gamma value. What's the gamma value? Gamma in thermodynamics is simply Cp by Cv. The ratio between specific heat we call, the ratio between specific heat of two gases is what is called gamma. Ratio between specific heat of two gases is what is called gamma, right? Yes. Yes. Now what is the gamma for monoatomic gas? 5 by 3. How much is this? 7 by 5. 9 by 7. What's the last one? 4 by 3.
4 by 3.
Yes, 4 by 3 is the gamma value. Got it? So I hope you copied this. Have you copied this on your notebook? Please check it.
Yes, sir.
What is work done? What are the various processes that is possible? Isothermal, adiabatic, isochoric, and isobaric. Shall we?
Did it change, sir?
Yes, I am going to change. Just I am leaving it so that somebody can, if anyone pending copying this, let them complete. So I am keeping it. Yes, come on, come back. I hope you understand. I am going to start with isothermal, is it visible? What I am writing?
Sir, no, sir.
Adiabatic, we will adjust, don't worry. Adiabatic, yes. Isochoric, isobaric. So that we can complete everything in one stroke, we can complete. Isothermal, what is constant? Pressure can change, volume can change, temperature cannot change. Come on, what else? Come on, what else can change? Pressure, come on, isothermal process. Pressure can change, volume can change. Can you supply heat?
Yes, sir.
Of course, but etc. etc. What should not change? Change in temperature is 0, change in internal energy is 0. Got it? Change in temperature is 0, change in internal energy is 0. Got it? Isothermal, change in any thermodynamical variable without change in temperature means internal energy. Temperature and internal energy is closely related. You know that? temperature and internal energy are closely related, right? When the temperature changes, internal energy changes, right? That is what is internal energy. Come on. Adiabatic, what should not change? Come on. You should not supply any heat. You should not put it on LPG stove because it's an isolated system. It's an isolated system. It's an isolated system. Isolated. Isolated system. Come on, delta Q 0. What else can change? Pressure can change, volume can change, even temperature can change, even the internal energy can change. What should not change? Delta Q should be 0. Come on.
Delta V, sir?
It's allowed. You can change. Adiabatic change பண்ணலாமே பிரச்சனை இல்லை, right?
Yes.
Come to isochoric. Please come to isochoric. What? Delta V 0. Rest everything is okay. Pressure can change, temperature can change, internal energy you can supply, even internal energy can change, but work done is 0. Why work done is 0?
No expansion.
Whereas you can attach here work done. Work done can be there. Work done can be there in the previous two cases, but in this case work done is 0. Come to isobaric, pressure constant. Pressure.
That is because no expansion.
Yes, no expansion, dV 0. dV 0, change in volume 0. இங்க எழுதிருக்கே. Your work done is PdV. Work done is integration PdV. This fellow is 0, therefore everything is 0, right?
Yes.
Yes, come on, change in pressure. Come on. இங்க சொல்லுங்க, change in pressure is 0. What else? Volume can change, temperature can change, you can supply heat, you can change the internal energy, anything you can do, but pressure is 0. Then first law, delta Q is equal to delta U plus delta W. Delta Q is equal to delta U plus delta W. What is delta U? Delta Q is equal to delta U plus delta W. Delta Q is equal to delta U plus delta W. First law of thermodynamics. First law of thermodynamics. You, my dear kids, please put it on. Very good, Kanna, very good. Priyanka said work done is 0. Very good. Lakshmi Narayanan, please reply me. Lakshmi Narayanan, please reply me. Suhas, dP is 0. Very good, excellent, Kanna. Good, come on. Isothermal. Isothermal, what is 0? 0. Adiabatic, what is 0? Isochoric, what is 0?
Delta V.
Isobaric, what is 0?
Nothing.
Excellent, nothing is 0. Excellent, Kanna, nothing is 0. Got the point. Very good, excellent. Got the point. Yes, go ahead. Now, let us take this case, say isothermal. Let's take the case of isothermal, right? First isothermal ஆரம்பிச்சிடலாமா? சொல்லுங்க பார்க்கலாம். இல்லை என்ன கண்டுபிடிக்கலாம் முதல்ல isothermal? Delta Q, is it under constant volume or constant pressure? Isothermal. Is it constant pressure or constant volume? Isothermal processes.
Constant volume?
No, nothing. Just to befool you, I am asking you. No, nothing, because only temperature is 0. Change in temperature is 0. Only temperature doesn't change. Pressure should change, volume should change. Look at, pressure should change, volume should change. Yes, look at the diagram here. P is inversely proportional V. You can very well understand PV is equal to RT for 1 mole. Here this is constant, this is constant. Therefore, naturally P is inversely proportional to V. This is the case of isothermal. Come on, what is work done by isothermal? What is work done by, I am not going to derive it today. What is work done by isothermal? 2.303 RT log to the base 10, come on, V2 by V1 is the work done in isothermal. Is the work done in isothermal. What's the isothermal formula you have? PV is equal to constant, RT is a constant. So differentiate this, what do you get? By differentiating this, what do you get? PdV plus VdP equal to 0, is equal to 0. So what do you get? P is equal to minus dp by dV by V. What is this? Can you guess? Can you find it? What it is? Change in pressure by change in volume. Yes, this is what is called bulk modulus. It's a bulk modulus in isothermal change. Is nothing but pressure. Is nothing but pressure. So today I am talking to you in this room where the atmospheric pressure is 1.01 10 power 5 Pascal. What is the bulk modulus of air around me? Atmospheric air around me, around you. It is same because we have clearly proved that pressure is same as bulk modulus, provided you are operating isothermal process. Provided you are operating isothermal process. Got the point? You understood something about isothermal today? Come on, come on, come on. Put it on chat box, please. My dear kids, please put it on chat box, please. Come on, Kana. Yes. Suhas, can you please put it on chat box, please? All of you please put it on chat box so that I can understand that you really present there. Please, please put your fingers on chat box, please. I'm waiting, I'm waiting. Understood, very good, very good. Priyanka Vatini, Bhargav, Soy, Sivaruba, Afsal, very good. Soy, Sivaruba, others please. Harini, very good, Harini, Suvas, very good, yes, all of you, good, very good, Kana. Come to adiabatic. In adiabatic, delta Q is 0. You are not going to supply any heat. Your system is, Karthika, yes, thank you. Now, it is an isolated system. It's an isolated system. What is the relation? PV is equal to RT for 1 mole. What is not going to change? Delta U you will not supply, right? You won't supply any heat to the system. Will the temperature of the system can change? Of course, it can change. This can change. Then what equation we are going to arrive at? Last time we had a very simple equation, PV is equal to constant. We got a very simple equation, PV is equal to constant, last time in the isothermal case.
The heat is not supplied, then how temperature will change?
You use cycle pump now. Do you pump at your cycle? Yes. At the end, whether your cycle pump is hot? Yes. You did not put it on stove, you did not supply any heat. So that is the very principle of thermodynamics. You can create heat without flame, without heating it. It is possible. Where? Because that's what is first law of thermodynamics. Look at, you can heat it, you can increase the, what is heat? Increase in temperature, internal energy. You can increase the internal energy without heating. It is possible by doing work. Please look at here, by doing work, it is possible. Come on, now the given formula for this is PV power gamma equal to constant, where gamma is nothing but Cp by Cv of the gas what you are using, Come on, what's the graph for this? PV, the graph goes like this. So the graph is supposed to be more steeper than, isothermal. Suppose the isothermal goes like this, look at, if your isothermal goes like this, your adiabatic will go like this. This is adiabatic, this is isothermal. At any given point, who is having more slope? At any given point, adiabatic has got more slope. What is work done by adiabatic? What is work done in an adiabatic process? Look at, this is 0, this is work done. Therefore, work done is nothing but negative of change in internal energy. What is negative of change in internal energy? Negative of 3 by 2 or T2 minus T1. 3 by 2 or T2 minus T1 is the work done. So simple it is, if it is a monatomic gas. For diatomic gas, 5 by 2 or T2 minus T1, because this is change in internal energy. What is internal energy? Please go and check. What is the internal energy formula we derived on the other side? Please check what is the internal energy formula we derived on the other side. Yes, that's what. I am using 3 by 2 because I am using monatomic by time being, right. Therefore, work done is given by plus 3 by 2 or instead of T2 minus T1, it is T1 minus T2, right. This is what is work done in adiabatic process. It is work done in adiabatic process. work done in adiabatic process. This is where you want to one more method is there, I'll teach. Now come to isochoric process. Isochoric process. Work done is 0, change in volume is 0. Now PV is equal to RT, universal gas, which is constant now, volume is constant, R is already constant. Therefore, if you draw the graph between pressure and volume, your volume is a constant. This is what is graph. This is what is graph for what? Volume is a constant. Volume is a constant. This is graph. What is work done? What is work done? Since delta V is 0, right? Where in a isothermal bulk modulus polama, bulk modulus, change in pressure by change in volume by original volume. What is change in volume value?
The bulk modulus of adiabatic.
We'll come back to infinity because this is 0. Bulk modulus of isochoric is 0. Come back to adiabatic. Adiabatic bulk modulus evlo podlam. What is the bulk modulus of adiabatic? What is the bulk modulus of adiabatic? PV power gamma is equal to constant. Differentiate P gamma V power gamma minus 1 plus V power gamma into dP equal to 0. I am using red color for distinction so that clearly you can understand. What is common? Right hand side is 0, constant differentiation 0. Therefore, V power gamma and V power gamma gone. So, P gamma V power minus 1 plus dP. I am given a dV with it name. Let me once again differentiate this. Come on, P gamma times V power gamma minus 1 into dV plus V power gamma into dP equal to 0. Yes, now which is common here? What is common here? V power gamma, V power gamma. So what you are left with now? P gamma dV by V plus dP equal to 0. Therefore, P is equal to gamma times minus dP divided by dV by V. This is your bulk modulus. This is your bulk modulus. This is your bulk modulus, right? Is it right? Please check it. Yes, perfect. Pressure P. Please check everything I have done correctly. Adiabatic then gamma times, yes, perfect, that's right. Come back here. Next time come on, anyone help me? Isobaric, yes, you are right. Isobaric, yes. Isobaric please help me. What is 0? Nothing is 0. Nothing is 0. How much heat?
Pressure is 0.
Of course, change in pressure is 0, but pressure exists. Change in pressure is 0, but pressure exists. Got the point?
Yes.
Come on, Kanna. Delta Q under constant pressure. Come on. Delta Q under constant pressure. Go back to specific heat formula. Come on. Mu Cp delta T. Can any of me help me out with delta U? Delta U under constant pressure. Change in pressure is constant. I want to calculate internal energy. What is your suggestion? Come on. What is your suggestion? Come on. Come on. Very good. Very good. Mu.
Cp delta.
Why Cp? Cv. This is the tricky point in thermodynamics. This is the tricky point in thermodynamics. I will explain you. Don't worry. Mu. So the idea of this understanding is this is internal energy. This is internal energy, this is internal energy, this is internal energy. Internal energy is a function of, fill the sentence please.
Temperature.
Please put on chat box, internal energy is a function of temperature alone. Please note it down. Internal energy is a function of temperature alone, nothing other than that. So whether you calculate internal energy in under constant temperature or constant pressure or constant volume, either you can substitute from anywhere. What I mean to say, you calculate internal energy, change in internal energy of the gas in a particular situation from particular process. You can transfer it, post it anywhere you want in thermodynamics, because internal energy is a function of temperature alone. It's a point function, it's not a path function. அது எந்த வழியா போச்சுன்றதை பத்தி நமக்கு கவலை இல்லை. Our concern is only point function, initial, final. Initial temperature 30, final temperature 100, that's it. From 30 to 100, how do you go? You go by any means you want, but the internal energy is same. Because look at here, internal energy is constant, constant, constant. Only temperature matters. Only temperature matters. Therefore, you go from 30 degree to 100 degree by what means? Maybe isochoric, maybe isobaric, maybe adiabatic. For all of them, internal energy is same. See, I go from 30 degree to 100 degree by adiabatic. I go from 30 degree to 100 degree isochoric. I go from 30 degree to 100 degree isobaric. எல்லாத்துக்கும் internal energy ஒரே ஃபார்முலா தான். நான் சொல்றது புரியுதா இல்லையா? Yes or no? Please tell me on chat box. It's a very important point. This is a tricky point in thermodynamics. It's a tricky point in thermodynamics. Come on, you understand? Please chat box. Please tell me on chat box. Can I please? Please put it on chat box, my dear kids. Yes, you understand? Because internal energy is a point function. Look at here on the board. It depends only on temperature. I am waiting on chat box, please. It depends only on temperature. Therefore, you can post it anywhere from anywhere. எங்க வேணாலும் தூக்கிட்டு போலாம். Provided the temperature is same. Provided the temperature difference is same. Temperature difference is same. Yes, Kana, very good, very good. Suga said yes. Sai said yes. Others may please put yes. Others may please.
Capital Y CV, sir.
That is an easy way to understand. Because when you work on CV, constant volume, எங்க இருக்கு பாரு, இங்க இருக்கு பாரு, constant volume. இதில் உனக்கு என்ன advantage கிடைக்குதுன்னா, work done becomes zero. Very good question, Kana. Very good question. I appreciate that. Why I am using CV here? Why not, sir? Didn't answer. அதை மட்டும் பிடிச்சிட்டீங்க, மத்தல விட்டுட்டீங்க. Because the reason is, when you work under isochoric, when you work under constant volume, your work done becomes zero. It is removed from the screen. Now heat equal to internal energy. It is very easy to calculate heat. It is very easy to equate with the internal energy. Appo, when you do the experiment under constant volume, you supply 1000 joules of heat. You can take it granted the entire 1000 joule gone for
Conversion.
internal energy. Appo எனக்கு இங்க என்ன வேணும்? Look at, எனக்கு இங்க என்ன வேணும்? Internal energy. So I supply heat under constant volume. So I take granted that the entire heat that I supply gone for, come on.
Internal energy.
புரியுதா concept? This is a tricky point. It's a very tricky point in thermodynamics. திரும்ப திரும்ப இப்படி தான் யூஸ் பண்ணணும். புரியுதா உனக்கு? You got the point?
Yes.
Good, good, good. Here almost all the kids have said yes, yes, yes. Kartika, Sai, Bhargav, Harini, Afsal. Others can also do something typing. Probably they don't have that. Panlame, cell phone le panlame, right? Yes. I hope you understand now. This is the delta U. Then delta W. Integration PdV. So integration தூக்கிடலாம். P into V2 minus V1. Not a good idea. Once again, non-mistake பண்ணிட்டேன். Sorry. Work done. PdV. Work done. The best option is P V2 minus V1. You agree with this? This is a simple formula to calculate work done in the case of isobaric. You agree with me? It is so simple in isobaric to calculate work done with compared to anything else. In enga pathina 2.303 or RT something is there. When you come here you have to calculate something. But here it is 0 of course. But in this case it is so simple. Simply multiply your pressure with change in volume. Got over. Your problem got over. Why? Because pressure is a constant. Again, if you go for isobaric, once again, very easy to understand. PV is equal to RT for 1 mole, let us take. P in dV, can you differentiate R? Can you differentiate R?
R is a constant.
Constant, so dt. Therefore, this PdV, look at, interesting point. This PdV can also be replaced with, come on. Can also be replaced with, come on. R into dt. This is applicable only in all this, only in isobaric. Now, I want to take the same isochoric, this one, I want to continue with this, I want to continue with this, I want to continue with this. Come on. So, whenever you want to calculate internal energy, what can you do? Whenever you want to calculate internal energy, what's the best way to manage internal energy? Come on. What's the best way to manage internal energy? Come on. Taking constant?
Constant volume.
Yes, that's the best way to manage internal energy. That's the best way to manage internal energy, right? So, we are in a position to wind up in few minutes. We will do that. Please let me complete this concept alone before winding up. Actually, I planned today a lot. I supposed to have completed even Carnot engine and the other engines, but I could not. Anyway, come on. Now, I have a cylinder piston. I am heating it under constant pressure. Constant pressure. Cp. Delta Q under P is given. Come on. Delta Q under P is given by delta U plus delta W. I have been telling you what's the best way to manage delta U. Come on, yara solunga paakalam. Whenever you want to think about internal energy, think about constant volume. Because in constant volume, whatever the heat you give fully goes to
internal energy.
Therefore, it is nothing but delta Q under constant volume. Delta U. You understand this? I hope. Whenever you want to calculate delta U in thermodynamics, think about constant volume, because whatever the heat that you give in constant volume, 100% goes to internal energy. Yes, delta W, delta Q. Right? Of course, I hope you understand. What is delta Q? Mu Cp delta T equal to mu Cv delta T equal to work done PdV. What is PdV? Mu times R dt. You understand? PV is equal to mu RT. Differentiate. PdV is equal to mu times R dt. You understand this or not? Because I am working under constant pressure, don't forget, my pressure is a constant, R is a constant, mu is a constant. Then what are the variables? V is a variable, T is a variable. Clear now? So, now delta W, what should I write here? Come on, help me. That's all. Mu, mu, mu. Delta T, delta T, delta T. What I am left with? Cp minus Cv is equal to, what I am left with? Cp minus Cv is equal to R. The Mayo's relation. The Mayo's relation, right? So, whenever you heat the gas under constant volume, the entire energy goes to internal energy, work done. Good. Now I want to take a small Cp minus Cv is equal to R divided by Cv. Cp by Cv plus 1 equal to R by Cv. What is Cv? R divided by, come on, what is Cv? R divided by, come on, who is this? Cp by Cv. Come on, what is this? Cv is equal to R divided by
Cp by Cv is gamma.
Ama. R by
gamma.
Excellent, Kanna. We are going to get a beautiful result now, beautiful and easy result to understand. Come on. Whenever you want to calculate internal energy, namakku ennalla vadi irukku paakalama? Come on, help me. Neenga yaravadhu enakku help pannunga paakalam. Whenever we want to calculate internal energy, what are the easy ways we have? What are the easy ways that we have to calculate internal energy? Come on. Paklama, very simple. Delta U mu CV del T. You agree with me?
Yes.
Which is nothing but mu times
3 by 2.
yes F by 2 or delta T. You agree with me?
Yes.
This is also called work done modulus in adiabatic. You agree with me? Go back to work done in adiabatic. Adiabatic la enna delta Q is equal to delta U plus delta W. This is 0 aipochu. Adiabatic. What's your work done? Come on.
Minus delta U.
So the modulus form of this is readily gives you work done. You agree with me? In the case of adiabatic, not all the cases. In the case of adiabatic. Appo delta U is equal to mu. Ipadam magic. Come on. Civic bela enna ponnum?
R by gamma.
Yes, R divided by gamma minus 1 delta T is equal to mu F by 2 R delta T is also given by work done adiabatic. So, இதிலிருந்து நம்ம என்ன conclude பண்றோம்னா here and after wherever you want to calculate internal energy, use this formula which is also perfectly equal to work done by adiabatic. So, work done by adiabatic can be blindly taken as change in internal energy anywhere in thermodynamics. Got the point? Concept puridan pare, at least copy panne. When you do it to second time, third time, when you redo it, you will exactly get the point. I hope you understand. Because in adiabatic, heat supplied is 0. Therefore, work done becomes a modulus of change in internal energy. Why I am putting modulus? I don't want to confuse with increase, decrease, confuse panna virumbala. Therefore, I am giving simple way. So, modulus of work done. Therefore, the modulus of work done of adiabatic is given by change in internal energy is given by, come on, mu times R divided by gamma minus 1 into delta T, which is also given by mu times F by 2 times R into delta T, where F is number of degree of freedom. For monatomic 3, diatomic 5, triatomic linear 7 and triatomic non-linear it is 6. Clear now?
Sir, modulus of adiabatic means it will be modulus of internal energy.
I don't want to come. This is a very clear case, no doubt about it. Because it will give ulta, minus. Therefore, I want to avoid confusion time being. Clear now?
Yes.
Yes. Otherwise, you will ask me whether T1 minus T2 or T2 minus T1. Don't worry. Work done by the gas is positive, work done on the gas is negative. Go with that. Got it?
Yes.
Any doubt anywhere, Kanna? My dear kids, please put it on chat box YouTube. You are going to wind up. I am not going to teaching anything more than this. You understood today's class? Please tell me yes. If you have any trouble, any topic, please mention the topic so that next class I can continue with that. Please, all of you put on the chat box, please.
So, Newton's law, when will it be used?
Adangane, first I have to teach you conduction in solids, and then I have to teach you convection and radiation. So, Newton's law is nothing but radiation. You got the point? It's the rate of cooling. By radiation. No doubt, Sai Suruba, Suhas, yes sir, yes, Ishwar, yes.
All these three are cyclic process only, no sir, like conduction, convection and radiation.
We will wait for that. I am here to teach you cyclic and non-cyclic. I will definitely do that. Jyoti Krishna, yes, Bhargav, yes, Suhas, yes, Govindraj, yes, please. No doubt, clear, very good, Kanna, excellent Kanna. We will continue with this. Definitely at the end of the year, in another few months, when my dear plus 2 students go for any kind of entrance, we will score perfect centum in physics. Okay? I will increase my classes. I request only one thing, sit with a pen and notebook in an isolated room. Keep jotting down the points. I will not leave any topic without teaching, and will thoroughly teach and will do sufficient number of numericals. Definitely you will get centum mark, whether it is IIT JEE main or NEET, let it be CBSE exam. Nowadays almost all have become almost the same platform nowadays. So we will score very good mark, don't worry. Says Suhas has reminded me we have not done triple point of water. Thank you Suhas, definitely we will do that. Sir, could you please explain once more R of gamma? Okay, gamma, yes, I will do that, don't worry, Priyanka Vatini has asked, definitely will do that. But triple point of water, I agree with you, I completely skipped that area because I had to go for PT graph of the given material, PT graph of the given material. I slightly mentioned the difference. Now, I just mentioned at some point there is a difference between vapor and gas. That is the triple point where I need to explain triple point, because once I enter into triple point, I have to teach a lot of things like melting, sublimation, all those, evaporation, and then gas. And the most important point is in that the given gas can be liquefied, the given solid can be melt even without temperature. These are the magics we are going to see. You know, given solid, you can melt it without heating it. Do you believe that it is possible?
How?
It is possible. I am going to teach you, don't worry. That is slightly higher level. Suhas wanted that. Definitely will do that. That is called triple point of water. It is possible. Okay, that is called regulation. That is called regulation. REGE, regulation. We are going to do that. Don't worry. Thank you. Please remind me on WhatsApp also. We will do whatever the topics that is missed. We will definitely do. I think we may need one more class to thoroughly do this. That's what it goes like. Because here and there a lot of things are there. We will patch everything. Okay, Kanna. Probably next week we can have the class for that. Come on, Kanna. Anything else? Today evening 11th standard kids will have class for our regular teaching. Come on. Probably at 6:30 I am planning. Come on, Kanna.
Which one, sir?
Regular thermodynamics. Regular thermodynamics.
We'll be continuing the.
Yes. Varun, chemistry class is there. What's the doubt? Today you have chemistry class. It will continue. That's the reason why I am winding up now. Okay, Kanna. Okay. Tomorrow we may not have class. Tomorrow morning we may not. Tomorrow evening we may not have class. Tomorrow, Monday, GEM Physics classes may not be there. Monday alone. Yes. Tuesday.
As usual, we won't be having no, sir.
No. We had some special batches. No, 8:30 morning batch and all we had. But this tomorrow I am not in station. Probably we will not have class. Okay, Kanna. Okay. Bye, Kanna. Bye. Take care. We'll meet our next class. Bye.
Sir, on February 5th, I'm having exams, sir.
Okay, Kanna. Don't worry. We'll try to complete it. Everything. Okay. February 5th. February 5th annual exam. You mean?
No, sir. Pre-annual.
That doesn't matter. We'll complete it, Kanna. Don't worry. Okay, Kanna. Bye. All of you take care. Bye.
Thanks, sir.
Bye, Kanna. Bye. Bye, Kanna. Bye.